Hello, Math Humans. We're going to do E1 today. We're going to be continuing our algebra work, and we're going to be looking at linear functions versus exponential functions. Our objectives are that we're going to compare the two. All right. So if you'll remember, we've done a lot of work with linear functions. That means that they are a line, and their generic equation is y equals mx plus b, and they look like just a cute little line, right? The slope is the same throughout the whole line, okay? And so that would be a line and its slope. So we know for linear functions that they are going to grow at a constant rate, which means that the slope is the same everywhere. Okay? Couple of things to think about for an increasing function. As the x values get larger, the y values get larger. The y values go up. Okay, and this would be an increasing function because the x values get bigger, the y values are also getting bigger. A decreasing function would be one where as the x values get bigger, the y values get smaller. And so an example of a decreasing function would be that, because as the x values get bigger, the y values are getting smaller. So the next thing that we want to talk about is an exponential function. Which means we get to have great conversations in this chapter about credit cards. All right, an exponential function is not linear, and it is going to look something like either this or it's going to look like this, okay? This one is called growth because the y values are increasing. It is an increasing function. And this one is called decay because it is a decreasing function, meaning that as the x values get bigger, the y values get smaller. Okay? A couple examples to help you remember. For an increasing function, for an exponential function that's growth, this would be credit card debt. I love talking about this. Talk about it more as the chapter goes on. So credit card debt. Another way that I remember this one is for decay, it might be radioactive decay. So a radioactive isotope is going to continue over time to get smaller and smaller. Okay? Alrighty. An exponential function is going to be of the generic form y is equal to a times b raised to the x. So if we talk about what those variables represent, a is the initial amount. Okay, it's also going to be the y-intercept because that means that x is equal to 0. Okay, so your book would call this the vertical intercept. I tend to call it the y-intercept, but it would be that initial amount, so it's going to be your y-intercept. B is going to be the rate of change. If b is greater than 1, that means that it is going to be a growth or increasing. And if b is less than 1 but greater than 0, okay, you can't see that, sorry, my bad, then it's going to be a decay or decreasing. Okay, and so to be consistent, we'll call this guy increasing. Alrighty, this is the generic form of the equation. A couple of other things to note about the equation is that the x, your variable, is going to be in the exponent position. Alrighty, let's move on to examples. So for example number 1, it's going to say for the exponential function, lots of writing, identify the initial value a and then calculate b, which is the base, and then write the equation in the form f of x is equal to a b to the x. So for this particular example, we're going to be given a set of data. So I'm going to have x values and y values. So 0, 4, 1, 5, and then 2 and 6.25. Okay? So remember we talked about a is the initial value. It is also going to be the y-intercept when x is 0. So this value right here, the 4, is a. So we know that a is equal to 4 because that x is 0. So that would be the y-intercept. The values are getting bigger, so we know that it's going to be a growth. All right, so we need to find b. So far my equation is y is equal to a b to the x, and I know a. So I'm going to write y is equal to 4 times b to the x. We don't know what b is, so I'm going to choose a point. So I'm going to write choose a point, and I'm going to choose the point 1, 5. Remember that is an x and a y, and I'm going to substitute it back into this equation so that I can solve for b. So I'm going to write 5 is equal to 4 times b raised to the 1. Okay. I'm going to solve for b, so it's raised to the first power, which is lovely. So I'm going to get b is equal to 5 divided by 4, which is 1.25. And you can either leave it as the fraction or the decimal. Either is fine. So now I know my equation because I know a. I just found b. And so I'm going to write y is equal to 4 times the 1.25 raised to the x. So there is my equation. And they didn't ask for this information, but I'm going to tell it to you. Your b is bigger than 1, which means that this is a growth. And we can confirm that by noticing that my y values are getting bigger as x gets bigger. Okay? All right. Example number 2 says for the exponential function, I want to identify the initial value, which is a, and then I want to calculate the base, which is b, and then write the function f of x is equal to a b to the x. Okay? So a couple things to notice. When we solve for these individual pieces, like we did in the last example, over in the answer column, so remember on your test, you have an answer column. You want to write down everything that it asks you to find. So I would have written down a is equal to 4, b equals 1.25, and then y equals 4 times 1.25 raised to the x. That way it shows that you understand what each of these numbers in the equation represents. Alrighty, so if we go back to this example, again we're going to be given a table. So I'm going to have an x and y, and I'm going to have 0, 3, 1, 2.25, 3, 1.27, and then 5 and 0.71. So as I look at this, I notice that my y values are getting smaller. So that means this is going to be a decay problem, which means that b is going to be less than 1. Okay, so it's nice to look at our graph and have some initial things to know to help me look at my work to critique whether I did it well or not. My initial value is right here, so I'm going to write a is equal to 3. I need to go to another piece of paper. Okay, so I know a is 3, so my equation y is equal to a b to the x is now 3b to the x. So just like in the previous example, I need to be able to solve for b. So I'm going to pick a point. It doesn't matter which point you pick. Some are just easier than others. So for this one, I'm going to pick the point 3 and 1.27. And I'm going to substitute those into my equation for the x and y. So I'm going to get 1.27 is equal to 3 times b raised to the x, which is 3. So now I need to solve for b. So I'm going to isolate b. So I'm going to divide both sides of the equation by 3. So I'm going to get b to the third is equal to 1.27 divided by 3. And at this point, I'm just going to leave it like that. I'm not going to push buttons on my calculator yet. To undo something that's been raised to the third, that means that I need to do the opposite. I'm going to raise both sides of the equation to the 1/3. Because if I multiply 3, technically it's 3 over 1, times the 1/3, which is the opposite, the 3's cancel, and I get 1. So when I do that, I'm going to get b is equal to, and let me show you how to do this in your calculator. So if I turn my trusty dusty calculator on, I'm going to do parentheses, because you want to make sure that you put everything in parentheses. 1.27 divided by 3, close parentheses, and raised to the 1 divided by 3. Okay, there are other ways to do this in your calculator. I think this is just the easiest. If you have one of the little old black guys and you need to use, let me clear what's there, and clear. Let me make it a little bit darker because I think it's kind of hard to see. Oh, much better. All right, so now I'm going to do the same thing. I'm going to do 1.27 divided by 3, and I'm going to raise it. Notice on this one that I don't get that little box. So that means on the older calculators, you have to put the exponent in parentheses, and I'm going to do 1 divided by 3, and then I'm going to hit enter and enter on both. And notice that I get the same value. The way that I just manage my calculator looks a little bit different. So if your calculator is like mine, and it takes you up to the top, and it has a little box for the exponent, yeehaw, then you don't have to use parentheses. If your calculator has an older operating system, that means that you have to put your fractional exponent in parentheses. So notice you get the same answer. It doesn't matter. Okay? All right. So that was handy. So we get that b is equal to, if I get all my papers out of the way, 0.75. Okay, and remember we only have to round to 2 decimal places. So now I know that a was equal to 3, b was 0.75, so my f of x is going to equal 3 times 0.75 raised to the x. And remember we said originally that the problem was a decay problem, which meant that b had to be less than 1, and technically it has to be greater than 0, which means it can't be negative. And notice that that's what I got. I got a decimal, which is less than 1. So that confirms that it is actually going to be a decay problem. So a couple of things to remember before we move on is a conversation about slope. So for a linear function, the slope is the same throughout the graph. Okay, and remember we kind of had this discussion. The slope is the same over the entire line. So that means that the slope is y2 minus y1 over x2 minus x1. But for an exponential function, sorry, I can't seem to spell today. So I'm going to talk about the graph. So let's talk about this. The cool thing is that the slope is different at every single point along the line. And so you'll notice as I draw a series of lines, the farther I go, so as x goes this way, the y's increase sharply, meaning that the y is growing really fast. So that means that the slope here is pretty flat, and then the slope progressively gets steeper. So the slope gets steeper as x increases. And then if it were decay, it would be the opposite. But it's just important to realize that unlike a linear function, the slope is different at every point along the curve. Alrighty, we have another example, actually two more. So for example number 3, it says, how do you tell if a set of data is linear or exponential? And based on the conversation that we just had, I would tell you it's all about slope. Okay? And then we're going to make it a little bit simpler, and we're going to talk about it by rate of change. And we've done problems like this before, and remember it's new divided by old. Okay? So if I were given a set of data, x, y, and here comes my data, I'm going to have a -2 and 0.04, and then a -1 and 0.2, and a 0 and a 1, a 1 and a 5, and a 2 and a 25. So as I look at the data, I notice that it's really small and then it gets significantly bigger. So I would tend to think that this is exponential. But I want to compare, I don't want to make assumptions. So I'm going to do new divided by old and see what happens. So if I do, oops, this is a 0.2, my bad. If I divide 0.2 by 0.04, then I get 5, okay? So, and actually I'm looking at the y values, okay? So the change in my y values. So then I'm going to do it again, and I'm going to do 1 divided by 0.2, and I'm going to get 5. So the slope is the same here. And then I'm going to do 5 divided by 1, and I'm going to get 5. So notice that, and I'm going to write y values up here. My y values are changing by the exact same amount. So even though I thought it was exponential, that's not actually true. This is a linear function because all of my y values change by the same amount. Okay, so let's try this experiment with one of the other sets of data that we had. So let's do the problem that we just finished. So here was my x and y. So I had 0 and 3, and then 1 and 2.25, and 3 and 1.27, and 5 and 0.71. And so, and I'm going to put a little y right there. If I do new divided by old, okay, so if I do 2.25 divided by 3, so 2.25 divided by 3, I get 0.75, okay? If I do 1.27 divided by 2.25, if I do 1.27 divided by 2.25, I get 0.5644. And if I do 0.71 divided by 1.27, 0.71 divided by, I get 0.559. So notice that these new divided by olds, the rate of change for the y is not the same. So therefore, this would not be not linear because the rate of change is not the same. Therefore, and those three little dots that look like a triangle mean therefore, yeah, math. Therefore, this one is going to be exponential. Okay, so it works regardless of which type of function we use. Alrighty. So then we have one more example, and then we are done. So for the last example, example number 4, the directions are just going to say linear or exponential. Okay, so my data, here's my thing. I have 1, 6.25. Bring my computer back. Except every time I try that, I can't type. There we go. And then my second set of data is 2 and 7.81. I have 3 and 9.77, and then 4 and 12.21. So I'm just going to look at the new divided by old, and I'm going to only look at the y values. So if I do 7.81 and I divide by 6.25, I get 1.2496. And I wrote all the decimals down just to show you, okay? And then if I do 9.77 and I divide by 7.81, I get 1.2509. So depending on which decimal you round to, if I had rounded to the second decimal, it would have appeared that these two are linear. So I'm just going to check the last one just to be sure, divided by 9.77. So 12.21 divided by 9.77, and I still get 1.249. So this one is a conundrum. We're going to write that it's exponential, but to verify that it's exponential, you actually had to go out to more decimal places than just 2. So just a word of caution, sometimes you need to look at more decimal places. All right, my dears, that is it for today. I will see you soon.